All right, let's get started. For those of you who saw this countdown, that's me recording the screen. I recorded myself rather than use the online thing, and so, or the built-in UIC thing, so I can edit the videos if I make mistakes and that sort of stuff. So if you don't see the countdown, please remind me to record. Generally speaking, that's not needed. I usually wouldn't use the microphone. It sounds a little weird, but I had a canoeing accident last week, and I hit a paddle on my throat, and so I'm a little hoarse for a while. It's getting better. Okay, so welcome to CS450, Computer Networking. My name is Jacob Eriksson, and I'm a CS professor. This is a class about the internet. It's basically how all of the internet works. And the general idea is I want you to be able to, at least when you get out of this class, you should be able to explain most of the internet to your relatives and make sense, right? And also to an employer, and also to go make it a little better, the internet that is, when you get a chance. So we should get a pretty good overview of the entire system, and then some hands-on experience with the pieces that we can modify as end users. We won't get that much hands-on experience with the internet core because that's relatively tightly controlled. Let's just conventionally start with the syllabus, and then I'll spend the rest of the lecture kind of giving you a quick overview of the internet architecture as a whole. Right. We meet here. My office hours are Mondays and Fridays, between 4 or 5 and 10 and 11. That can change. We will have a piazza set up soon. I just haven't gotten around to it, and I'll sign you all up for it if you're registered for the class. If these hours don't work for you, and you're the only one, then we'll keep these hours. If they don't work for many of you, you have conflicts, we'll figure out some other hours. We'll just do that over Piazza. And we have 2 TAs. Our grad TA is here today. Hamed, you want to stand up? So Hamed will be helping you out with the many and difficult homeworks, and he's also helping he'll be doing most of the homework grading, and so you want to talk to him when you think there's been a mistake in the homework grading. We don't know when his office hours will be just yet, but it'll be Tuesday and Thursday at some point, probably after lunch.
Yes.
And we don't know where quite yet. So. There's also an undergrad TA, and I will ask him to swing by on Wednesday. You can stick around or you can take off if you want.
Okay.
Yeah.
Thank you so much.
No worries.
See you later.
Okay, so the course textbook, I didn't bring it, but this is a mandatory textbook. It's computer networking, a top-down approach. You don't have to get this $140 whatever book. Just get some older version. We're not going to follow it that closely, but you need a reference that covers everything. And I will say, now you should probably be reviewing the network layer section or chapter of this book. So it doesn't matter which revision you have, but yeah, try not to get one from 2000. So maybe revision. This is 7, I think, so 6 or 5 should be fine too. Right, and the other one that could be handy is the C programming language. All of our homeworks will be in C, or at least on the Unix command line, if there isn't any programming. This classic C programming language is just a short reference of C. I like it a lot. But you don't need to buy that one. You can take a look at it in the library if you need it. In terms of prereqs, you need 361 computer systems. That is an intensive C programming course, and as is this one. So that should give you most of the background that you need. And just in terms of getting your programs written. We will also be using some standard tools like Git for revision control and for submitting your homeworks. and we'll have a bunch of Unix command line sort of things, most likely, in the homeworks as well. So if you feel very unfamiliar with the Unix command line, this is the time to brush up on it. I can recommend, if you haven't taken 361, I can recommend online lectures. They're all recorded, at least my online lectures are all there from 361 in the past, and I think the other professors as well do that. So you could just review that and get up to speed if you want. Right. In terms of academic integrity, the point of these homeworks is to get lots of hands-on practice with writing programs in C that deal with networking stuff. Right? And so you are to write the programs yourself. There will not be group projects, and you are not, the intent is not for you to work on a project together with someone else, that is, work on the same code. Right? But it's perfectly fine to discuss how you are solving this problem or things you're running into. The best is if you can discuss it on Piazza. That way others can benefit, and also I and TAs can keep a little eye on it and let you know when something is getting inappropriate. Right? If you're just doing it with your friend, then it's harder to tell, and at some point maybe some plagiarism concerns show up, and that can be really hairy. Right? So plagiarism, for those of you who are not familiar, I think most of you will know, but here that means copying code or writing off code from someone else. Right? It's not just copy-paste. The idea is you write your own solutions, but you can discuss the methods. That's fine. If you do end up copying anything wholesale, sometimes it feels like, oh, this is just boilerplate. Right? I'll just get it off of Stack Overflow. That's actually okay. But if you get it from Stack Overflow, put a reference like this. Right? So now we know where you got it from. We know you didn't copy it from a friend. You made it public what you did, so it's not like you're trying to cheat. You just thought that this was okay. And so now we make the decision whether or not to give you points for it, but we don't make the decision whether or not to try to get you kicked out. Right? Nobody wants that. And so just keep it on the books, and it'll be fine. So same thing if you're getting something from Piazza, you could say from this Piazza post, or anytime you're copying code, just make it clear where you got it from, and everything will be, if not full score, at least safe. Right, so that said, the exams will also be closely related to what we're doing in the homeworks. And so if you're getting too much help with concepts as well, if you're not figuring things out on your own, you're probably going to suffer in the exams. So the best way to kind of study for the exams is probably, in most of the topics at least, is to do all the work yourself and really dig into the homeworks and try to go above and beyond. Not just in terms of getting everything right, but understanding how it all fits together. That's sort of the goal of the whole class, right? We want to know how this enormous machine, that's the internet, how that all fits together, and it's not that easy of a job. Right, grading, we've got 2 exams, the midterm and the final. Midterm's worth 20% of the grade, finals 30% of the grade, and then the homeworks. And we don't quite know how many homeworks it'll be, but there'll be many, probably 7 or 8. They will make up 50% of the grade in aggregate. You should note that the exams tend to be difficult. Right? It's not that, oh, I'm an A student, so I would expect to get at least 90% on the exam. Well, some A students will get 90% on the exam, but you might also get 70% on the exam and still get an A. Right? Depends. It changes every year, but my mean and median on my exams tend to be around 50%. And so that doesn't mean I just give a bunch of C's to everyone. Right? It's just I get a good spread and I get a good mean. This is the most I can get, most information I can get out of the exams. So those people who get 95% on the exams, they usually end up getting jobs in my lab or jobs with my old students at the top places in computer system stuff. And for the rest, I try to be a fair grader. Okay, yeah, so in terms of the curves, we set this after all the results are in. Usually it's pretty clear. Like you can tell, oh, these people, they really know what's going on. These people didn't even try, so those are the A's and the F's. And then usually there's a pretty good big groups of B's and C's who are kind of somewhere in between. And the cutoffs are usually not hard to set. There's like these natural groups, and I don't know why. Okay, before we move on to topics, any questions so far? Yeah. So
the website that we'll be going to is CS450.red.uic.
Yeah, it's not active yet. It'll say cs450.class.uic.edu. The assignments will be on there. All of the lecture recordings will be on here under schedule. It's kind of rough still, this class website. But, and then we'll have a link to the Piazza as well. Turn-in will be with Git over, what is it, Google Classroom, I think. Oh, is it? No, it's GitHub Classroom. But that'll be later. I don't use Blackboard for anything, so you'll get your results over email instead. Okay, so things we're going to cover. Basically, the internet, it can be described in many different ways, but we'll try to cover all of the various pieces. So that means the conceptual layered network model, a bunch of various applications and how they work. The layers being the physical layer, kind of how the cables work, how the radio works a little bit. And then on top of that, how you share the cables and the radio with many different users. On top of that, how you create a local network out of many such links, say a home network or a campus network. And then above that, now we're at layer 3, the inner network layer, is how the internet actually puts together all of these small networks into one large inter-network. That's the internet. That's IP addresses, which you've probably heard of, and routing and such. And then on top of that, the internet is actually a very unreliable, at least by design, an unreliable network. So it'll often drop packets. You try to send something and it just drops what you tried to send and it doesn't tell you about it. So how do we actually get a reliable connection over this unreliable network? That's the main topic of the fourth layer, which is the transport layer. You may have heard of TCP, Transport Control Layer Protocol. There's other protocols there too. And then the fifth layer is the application layer, and that's like the web or email or Skype and that sort of thing. Those are all different applications that run on top of the transport layer, which runs on top of the network layer, which is on top of the link layer, which is on top of the physical layer. And that whole stack is something that we want to have a good grasp on. And it's not like it's all perfectly layered like that. You go up and down a whole bunch of times before everything works. But we'll get all of that. Okay, we'll deal with mobility a little bit. Like you're moving around with you take your laptop from here to home. What does that mean in terms of routing? A little bit of cell phones and a little bit of security. And then, yeah, I think that's about it. Questions before we go and do a little demonstration? Yeah. No, okay. Other questions? All right. So I thought, why don't we take a look at the most popular application, the web, for a moment, and try to see if we can get some rough idea of what's going on under the covers there. Oh yeah, I should also make clear that I don't use slides. So every lecture is going to be like this. I'm going to maybe type a few things on here. I'll draw some ugly pictures with another program. I will, now I quit my web browser. We'll do a whole bunch of web browsing and doing things on the command line and looking at code and that sort of thing. That's what the lectures are like. If you don't like that, too bad. Try next semester. And that also means that class notes are basically what you get is what I type over here in the pictures. If you want to take notes along the way, that can be useful. I'm also recording everything. It's often useful to review, especially when I'm doing demonstrations. It's useful to review those videos, maybe go at half speed, try to repeat some of the things I'm doing, and, to get some more of the details along the way. All right, so why don't we take a look at this popular website? And I guess most of you have seen what happens if you say view page source, right? Who hasn't seen this yet? Okay, very good. Everyone has. Great. So, but where did this all come from? Right. So I typed in this address, www.uic.edu. Okay, but this is a web browser, but we don't have to be a web browser to talk to a web server. So let's talk to the web server as people instead. And a good program for that is called Telnet. Who's used Telnet before? All right, a few of you, very good. Telnet is a plain text. Well, actually, most of you have taken 361, right? Who didn't take 361? Oh, wow. Okay, excellent. So, and I know you know this stuff anyway, so that's fine. Noman is my PhD student, and I kind of made him take this class anyway. Okay, so Telnet, all it does is establish a socket. Right? You're taking 361, so you know, make a socket, you connect to this address at port 80 is what we're going to do. But Telnet, you tell it which port, you tell it which address, tell it which port, it connects to it, and then it tries to read from the other side. If anything's there, it prints it. And then if you type anything, well, it sends it over the socket. That's it. That's all Telnet does. And there's some little command mode. But so let's take it for a little ride. Is this visible from the back? Go a little bigger, maybe. Yeah. Okay. So here we are talking to a web server, and in fact, since you've taken 361, I just talked to Professor Kanish. You've probably dealt a little bit with a little web server in the past. Maybe you implemented a basic web server. So let's quickly go do this thing then. Okay, so the simplest thing you can ask a web server for is this, and that should be pretty much the same thing that we got in here. Let's take it from the top. Bottom will be easier. Same stuff. All right. Okay, so, but how did this get here? There's two curious things going on here. One being the port that just says which program you want to talk to on a web server. You've done that. And then there's the name here. But the name actually doesn't mean anything to the internet. Yeah?
Wait, isn't it get/HTTP?
Yeah, we can do it again. So it's like that, right? So the command is get. This is just the HTTP protocol. And we'll talk a little bit more about protocols later on, how they're defined, where they come from, where you can read about them. So there's a command called get. We say which file you want. This is basically the root document of the whole server. And then I went with HTTP version 1.0. That's really primitive. Usually they go with 1.1, which has a lot more fancy features. Anyways, you tell it that, and you get back the document. Oh, extra empty line after. Right. Okay, so there's that. But now we have this this name, and the name doesn't mean anything to almost any of the internet. Right? There's lots and lots of pieces along the way, switches and routers and cables and Well, I guess those are the main things. Lots of them, though. So we need to get from the name to an IP address. So we won't see all of the pieces, but if I say this, we'll see at least a little bit of the internals. So this is the actual location from an internet perspective. If you know this address, the IP address, internet protocol address of the server we want to talk to, you can tell any IP equipped device out there, like send a packet to this address and it'll get there. That's what the internet protocol does. That's basically its only job. So you have to get from this name to this address, and that's actually just an application. That's sort of like a web server. It's just an application that uses the internet protocol to send things back and forth. I think we can probably, yeah. So the way it works, just to quickly take a look at that, so I was looking for this name. My computer is configured to know the address of a server that can resolve names to IP addresses. So here it's told that, oh, we have a name server over here that if you send it a name using the DNS protocol, different from the HTTP protocol, then it'll tell you back the IP address. And once you have the IP address, you can go on your merry way. How does that server know where what the correct IP address is for billions of DNS names, or at least hundreds of millions? Well, that's a whole big complicated application that we will explore in great detail later on. In fact, you'll be implementing a little DNS resolver yourself. But the general idea is give it a name and you get a number back, so that's great. Okay, in fact, let's see if we can do one more thing. Okay, so now I started this little program called TCP dump. It's just listening to network traffic on my machine. So I thought I haven't practiced this, so we'll see how it goes. But okay, right. So now I connected. In fact, we'll just stop right there. So I connected to the web server, and TCP dump saw a few things happening. Right. So here, in fact, I think, let's do it again, but we'll do it with numbers instead, with numeric addresses. Start over. Okay, so we're basically spying on the traffic that my telnet client is creating. And there it is. Okay, so we connected to this thing, and here's the first packet. A packet is a small little bit of information that you can send over the internet. Usually it's no bigger than 1500 bytes. So you can send 1500 bytes, you can send another 1500 bytes as many times as you want. But it says something here, that's me, from some port address, source address, and you may recognize this IP address, here it is, right? What we're trying to talk to. And then port 80. And in the first step here, this is TCP, the transmission control protocol that is establishing a reliable connection over this unreliable network. It's called a SYN packet. It's an initial sort of setup packet. And then we get a response. So you see here, this is from my laptop to the server. And then comes a response from the server saying, yeah, okay, let's talk. Right? And then again from my laptop saying, okay, so now I know that we're set. It's called a three-way handshake. I send a connection request, I get an acknowledgement back saying that's okay, and then I send another acknowledgement saying, okay, I hear that you heard me. Right? So now that we've gone all those three steps, now we both know that we've agreed that we're going to have a reliable connection. There's a sequence number in here. They start at some random number. But then when I send another packet, I increment the sequence number by the number of bytes, so that next time if they get another packet from me, and it doesn't fit the sequence number that they thought they would get next, they will know that, oh, something's missing, and they'll let me know and I can retransmit that packet. That's how you get a reliable connection. Okay, okay, and then there's just the rest of the reads and the writes, and we can sort of ignore that. Let's see if we can get maybe one more step down. How do we do this? There it is, E. So, okay, so I asked for some more detail. Same thing again. Oop. Okay, so here, these are again the IP addresses, but here's something more now. So we're snooping on the traffic that's coming from my laptop and going out, and whatever's arriving into my laptop. We can't see anything what's going on at the server end, right? We're just seeing what my network interface, in this case a wireless interface, is receiving and transmitting. So here we're seeing this is coming from my network interface. It has another address. Right? This is the local address, or called a MAC address. So just a unique identifier of my wireless, my Wi-Fi adapter in the laptop. This one doesn't change. Well, you can tell it to change, but it comes with a number from the manufacturer, and it's globally unique. And then it's trying to send it to another MAC address. And this one is the next hop. It might be in here. It's probably that one, right? Or maybe that one. Or maybe that one. Holy shit. Is another one there too? No, that's a speaker. No. Anyway, that's a lot of Wi-Fi access points. Good job, ACCC. I wish they would do that in my office. Anyway, where was I at? Yeah. So I'm sending a packet here, and all I'm saying is, like, okay, let's try to get a packet from my machine over radio to over there. Let's pretend it's that one. And that's it. And then inside of the packet, and we'll see that's some more detail, but basically the packet starts, the first few bytes say this. It says, this is the address it's coming from, that's the address it should go to, or maybe it's the other way. Forget the order. And then it says, oh, and I'm talking internet protocol here. That means that whatever comes next, the next header, the next piece of the packet will say, oh yeah, I want to go to this address, this internet address. Right? So once it's received over there, it's the access point's responsibility to take a look at the inside of the packet to see what it should do next. This assumes, and there's some various variations here, it's not entirely clear that this is the address of the access point. It could be the access point is just a dumb radio, and this is the address of a gateway that is another piece of equipment that is kind of more centralized. Maybe it's for the entire building or even for the entire East Campus. Seems unlikely. We could go to another classroom and try. If it's still the same address here, that means probably wasn't the access point. It was probably something a little further down the road. Okay, anyway, so the first step was, or the bottom layer that we can observe here is this MAC layer, or the link layer that says, what is the next hop? Just get there. And then inside of it, it says, what's the final destination? But it doesn't say anything about where we should go from there to the next, like somewhere in the building, to somewhere at ACCC, to somewhere, and so on. That's not specified. It just says, you take it next, and then make sure it gets to over here. And that's sort of the design of the entire internet. And inside of this then follows, so now we had the MAC part, the MAC addresses, and then we have the IP addresses, and then we have the TCP stuff with the sequence numbers, and also those ports, like the 80 and stuff, some other things. And after that, in this case, probably comes the HTTP payload, where we say get space / space, right? That may show up in, well, I didn't actually type it, so it didn't show up, but yeah, that would come after the TCP header. So all of this comes together as one chunk of up to 1500 bytes. If you can't fit it, like that web page, it doesn't fit in 1500 bytes. That was a lot of CSS. And so then it'll send another one that looks just like this, again with like next hop. The internet doesn't remember anything. So you just tell it, again, go over there and then make sure it gets to the final destination, and probably you include a new sequence number. Every packet is treated independently. There's no connections set up or anything like that from the internet's perspective. But of course, from the web server's perspective, we did set up a connection. We had this agreement, right, that we will communicate over the unreliable internet for a little while. Okay. Questions on that before we move on? So because my lectures are like this, just kind of going off on random directions or somewhat guided directions, right? I very much encourage you to ask questions along the way, and maybe that'll make the lecture more interesting because we'll talk about something completely different. Right? So the entire semester, you can pretty much just, it's like a choose your own adventure sort of thing. Usually those books, they kind of have all these shortcuts that get you to the same place at some point, right? It's going to work a little bit like that, but yeah. So make sure you take advantage of that. It makes everything more fun. Yeah?
If you didn't use Telnet and you just connected through the web browser, would you still get all this information through TCP jump?
Oh, yeah, but it would be a lot more messy. Let's do it. Oh, look, it wants a password again. Okay. So let's go to the same place. Yeah, okay, so it got a little messy because there was many packets, but let's start from the top. So that's the old one, right? And the first one here, you see it's from the same MAC address, naturally. The web browser doesn't identify itself there. It does identify itself to some extent over here. That's the port, right? The IP address will be the same, right? It came from the same machine. The IP address identifies a machine in its current location. Not a machine in general. Like if I bring my laptop to my home, it'll have a new IP address. It'll still have the same MAC address though. Right, so yeah, we have the same kind of setup part because the web browser used a TCP, but after that we got more because the web browser made a long request and got a long response. Yeah?
Can you get, how do you get to display IP version 6, or can it not?
This one cannot because the UIC web server doesn't support IPv6, I believe. And I also am not sure that we get IPv6 connectivity here. Generally speaking, though, you would just type in, well, when we make the telnet connection, you could type in IPv6 address there, and everything would work the same. TCP dump would output the longer IPv6 address instead. Not a whole lot of differences between v6 and v4 except for the length of the address. Yeah.
So where is the size of the packet in that printed out?
Here.
And each one's different?
Well, not really. There's depends a little bit. So these could be acknowledgement packets. Basically, I'm telling the server, yeah, okay, I got it, right?
So is that
Those are
bytes?
short. These are in bytes, yeah.
Okay.
So why does it take 66 bytes to say I got it? Any ideas?
You guys said the address, like where you're coming from, where you're going to.
Yep,
right?
exactly. There's always all these headers because otherwise the internet just can't bring it to the end. It's like you send a letter. The internet is a lot like the USPS. You put a name at the top. We don't do that in the internet, right? But the rest of the address is very similar. Part of this address is sort of the country part, right? Not really country, but it's a large network. This one isn't a good example. This one is a good example. In fact, let's take a look at that. So you can tell a lot from the address. This is a 32-bit address. It's 4 pieces of 32 bits each. Oh, sorry, of 8 bits each. We write it like this. It's just how it is. the IPv6, the newer version, which is getting more popularity, but it's a really, really slow transition, has 128 bits instead, so it becomes a longer address. Sort of the same idea. So if we say this, we can learn something about the network, the larger network that this server belongs to. So this part, it basically says UIC. Right? There's, how many of these are there? Anyone? How many such prefixes are there? Yeah, there we go. 65,536. Roughly. There are some addresses you can't use. But yeah, so, and UIC has one of those. In fact, UIC has more than one. That's pretty good, because there's a lot of organizations out there who would like to have their own subnet like this, and this is a big one. Okay, so let's look at it. Here, this entire range, so 65,000 addresses, belongs to, well, it's called UIC Net, and it belongs to the University of Illinois Chicago. And I think if you check the med school, you'll find, in fact, let's see, does anyone have a host name for a med school? Like, is it pharmacy.uic.edu, or let's see. Okay, no, that's the same prefix. Anyway, there used to be two. I'll look it up some other time. Okay, so we can see sort of who owns that entire part of the internet. Every address that starts with 128.248, that's us. So that means that if you're somewhere across the world and you're getting a packet that says 128.248, you don't need to know about UIC's web server. But you do need to know about UIC. Right? You have to actually remember, oh, this prefix, that means I should send it to that next hop. That's all you need to remember, but it's still, non-trivial. Of course, if there were only this, if all the prefixes were this small, so there's only 65,000 of them, remembering 65,000 next hops, that's easy. But many prefixes are more like this. So then it's 24 bits. That's 16 million prefixes. It starts getting a little annoying because they do change relatively frequently. And there's prefixes that are even longer and more unique. So there's a lot of stuff to keep track of if you want to be a router. That's what a router does, at least a general purpose router. Knows where everything is in the internet. Yeah, those are annoying. Most of us, though, just send it to the next hop. Like if you have an internet provider, you have one internet provider. UIC has a bunch. But if at home you have one internet provider, well, it's pretty easy to do your routing. Because you know the next hop is going to be them. Right? There's no other place to go. So you just send everything that starts with anything to your internet provider and you're set. So that kind of router is easy. That's what the sort of the Wi-Fi router that you have on your desktop, that's what it does. It remembers what your local addresses are, some small range of private addresses, and then the rest send it to the internet provider. Okay, I wanted to do one more little demo. Let's send email. So email is not a web application. It's, at least for the layman, so to speak, it's easy to think that the web is the internet. But the web is one application. It's HTTP, plus some HTML, kind of pretty pictures, that sort of thing. But in terms of applications, it's that protocol, HTTP, and the HTML standard. That's the web. Everything else, TCP and IP and the various Wi-Fi and such, has nothing to do with the web, and every other application out there uses the same technologies. Email is one of the original. DNS is one of those applications, by the way. Has nothing to do with the web. Email is another one that sort of showed up before the web did and is still around. A lot of people use Gmail and then it feels like it's a web application, but that's just a mail client that happens to be served over the web. Okay, so if you want to send email, what do? Well, you have to talk to some host, to some server, on some port. The port is predefined, just like with HTTP. It's port 80 for the web. Port 25 is for email. So I want to send an email to me. my CS address. So my CS address goes like this. Oh. So the email protocol is, you can specify destinations with a user, an @ and then a DNS host name. But this is actually not a mail server. cs.uic.edu is not a mail server. It's just some general domain, has all sorts of stuff. If you want to talk to a mail server, you should be a little more specific. So you can tell the DNS, the domain name service, you can tell, I'm interested in a mail server for this domain. So I'll say MX for a mail exchange. Okay, so mail is handled by this machine. So let's talk to it. So now we're talking SMTP, Simple Mail Transfer Protocol. This is what all email uses, basically, to go back and forth. Except if you are talking to a mail server and you want to get whatever's in your mailbox, then there's another protocol called IMAP or POP. That's just to talk to your mail server to kind of deal with your mailbox. That's not the email protocol. Okay, let's talk to it. So first you have to introduce yourself. It's an old protocol. They used to be polite. And so I want to say, who's it from? So we're an outsider now, outside UIC. We want to send an email to me, right? Who are we sending from? Right, so we're sending an email from the president, and it should go to me. Interesting. They had a little gray listed for 60 seconds. I guess I've done this once. I tried this just the other day, and okay, let's do it one more time. 60 seconds. I don't remember what the standard is, but basically this little thing makes it expensive for spammers because they have to keep state for 60 seconds. So just having this little extra delay means spammers won't get through as often. It's an old idea, but let's try again. Now it's gone 60 seconds, I think so. I typed too fast. Okay, now it should work. Thank you. I'm glad I remember that. Okay, so we sent the email, and the point of this, well, I wanted to demonstrate two things. One is that you don't have to be anyone special to talk mail. I mean, people can do it. You don't have to be a mail client. Most of these protocols are plain text because it makes it easy to debug. It makes it easy to write new programs, and it's just generally a good idea. Okay, but that email got sent. So let's actually see if we can find it. So I like to use a normal one. Oh, there it is. Okay, so that's another important point here. And maybe I should hide the rest of it. But basically, email is unauthenticated. Right? So anyone can send email from anyone else. Don't trust it. Good to know. It needs to be encrypted. Yeah. I don't know if that's his actual email address, but it would go to him. Oh. Yeah. So I wouldn't. It'd be better not to. Anyway. And another important thing, we didn't run TCP dump on this now, but if we were to run TCP dump on this thing, you would also see all of that text as it made it over the network. So if you're using someone's open Wi-Fi access point, or encrypted Wi-Fi access point for that matter, using someone else's network, and you're using a mail client to send an email, they can read it like a postcard. It works the same as postcards, right? You give your postcard to the mail carrier, and it gets delivered. It's fine, but the mail carrier can read it too if they want. If you want an envelope, you have to encrypt it. It's, okay, we're out of time. Yeah.
The email you sent it from, the email address you sent it from is not actually yours, right?
I am not the president,
Yeah.
and I don't want to be.
So anytime you receive an email, there's no guarantee that the email address is valid.
Yeah, absolutely not. Yeah. Okay, so that's just in the nature of the email protocol. The internet doesn't know about these things. I'll see you Wednesday, and then we'll talk about homeworks.